in this force problem homework, your first situation was some dude standing on a scale in an elevator. And we're told that uh, his mass was 100 kilograms, told that his initial speed was 3 meters per second, comes to a stop, so its final speed is 0. That means my change in velocity is going to be minus 3 meters per second. So right off the bat, um, we obtained that. And then we also know that the change in displacement, and which happens to be in the y direction, was 2 meters. He was going up, as I recall the problem. Moving upward at 3 meters per second, but stops after traveling 2 meters. So we, here's the person. They're standing on a scale, so this is a system schema. The Earth is involved. So there's a contact force between the person and the scale. There's a gravitational force between the person and the Earth. There is between the scale too, but we don't really care that much. So there's two forces involved in this situation. And so if I were to draw a force diagram, I have the weight of the person pushing down. So this is about the person, right? Always the point particle version of that. And then as we learned earlier, there is this normal force instead of contact force of person on scale or scale on person. It's this surface reaction force. That's what a scale measures. And so, and we know that the acceleration is non-zero, but the direction of the acceleration is down. Okay? And the reason for that is that my change in velocity is negative, or it's less than 0. That means the acceleration is downward. So elevator person in the elevator moving up, but they're slowing down. Hence, that's a deceleration, or what would be a negative acceleration for us. And so when I go to sum forces, okay, sum of forces will be the normal force, which is upward, minus the weight force, or mg, downward. And the sum of forces has to equal, let me go back here and change colors. So here is the sum of forces, N minus mg. And according to Newton's second law, that always has to equal ma. So sum of forces, this is what we're, sum of forces. That's what that symbol is dealing with. So if we wanted to, that's what that means. Sum of forces, that highlighted part, equals ma. Oops. So if I take, if I wanted to say know the uh, normal force, then this is going to mean that normal would simply be ma plus mg, which means it's going to be m times a plus g. Problem is, I don't know what a is. I know what little g is, and I know what the mass of the dude is, but I don't know what the acceleration is. That's why I suggested that you use the graphical analysis. So we have, make one big axis here. So here's time, here's speed. Actually, I'm gonna move my axis here. Since I know it's a negative. So this is our acceleration graph. And according to the data, started at 3 meters per second. Down to 0, which means our acceleration is a negative acceleration of some sort. We know that this delta y was 2 meters. We know that delta v has to equal a delta t. We also know that it's a minus 3 equals a delta t. But we're sort of stuck with that. But up here, we know this 2 meters equals 1/2 delta v delta t because that's the area formula. We know that delta v is a minus 3. So that means our delta t is going to be basically 2 times 2 over negative 3. And we just take the magnitude because we're talking about this height. That's what delta v is. And so that's not a negative height, all right, for what we're doing. So we just, with time calculation, so 4/3 of a second is what is happening here. And that means the acceleration, okay, is going to be just delta v per delta t, or 4/3, I'm sorry, let me back up here, 3 over 4/3, so my acceleration ends up being 9/4. Now, it's going to be a negative 9/4 because it was downward. And so then we can finish our thing here. So 100 kilograms. And we're basically, it's going to be, if you wanted to, you could use the 9.8, but you're going to have 10 minus 9/4, roughly speaking. And so you would get a normal force of basically 1,000 kilograms. So if it's 100 kilograms times 10 newtons per kilogram, if I'm using the rough number, 9.8 obviously be different, then it would be 1,000 newtons or 980 newtons if you're using the precise version. But then you're taking away some of the force because in decelerating, the surface contact force is going down by some amount, okay? And it's going down by almost a quarter of the true weight. So you end up getting basically 1,000, and 9/4 times 100 is, or times, and so your normal force would just be 775, right? When you take that away. So that's what the scale reading would be, 775 newtons. I mean, if you could convert that to pounds, 1 newton is roughly a quarter pound. So you could, obviously, it's not 775 pounds, but 775 newtons, which is our unit for these sort of things. So that's the gist of number 1 in the homework. Any questions on that? In problem number 2, we had a ceiling and a rope hanging down above the ground, and then there was a person hanging on the rope. And we're told that the mass of this person was 40 kilograms. Speed initially was 0. Speed final was 1.4 meters per second. And so what that means is my change in speed is going to be 1.4 meters per second. We're told that the time involved with that speed change was 2 seconds. And so that means that I could immediately go to the acceleration. Delta V per delta T is going to be 0.7 seconds. So now we know the time frame over which this change occurred. So if we were to draw a system schema, so we have a rope, we have the person, and we have the earth, rope and the person in contact. Not going to do the rope and the earth because that's not going to matter to us. But we have that system of the person, and there are 2 interaction forces on that. So if I were to draw a system schema of the person, we know that person has a weight force going down, or mg. It's a really lousy G. There we go. And then there's rope force, or what I would call tension. We like to use capital T for that. That's pretty conventional. And we are told that this person changes their speed in the positive direction. That would mean a positive acceleration, or moving upward acceleration. And so my sum of forces is going to be tension up minus weight down equals ma, which means tension is ma plus mg. And so we have, let's see, 40 times 0.7 plus 40 times, I'll just use 10 for ease here. So 0.70% of 40 is going to be 28, and that's going to be 400. So the total tension in the rope is 428 newtons. If the person was just hanging there, it would just be tension equals mg. That would be the tension in the rope, but obviously if you start pulling on the rope, that has to increase the tension in the rope. All right. Now, just to bring in the impulse momentum theorem, F delta T equals M delta V. If I solve this for force, all right, then I'm going to get 40 times 0.7. Oops, that's not correct. That's acceleration. 1.4 over the 2, and I'm going to get 28 out of that. All right, because that's just 40 times 0.7. Reason I'm doing this is I want you to notice that those things are the same thing. So I had suggested on one of the other problems, and I gave a warning with it, if you remember, that how you would use the impulse momentum theorem. And so does the impulse momentum theorem apply to this problem? Yes. Does it give you the answer you're looking for? Part of it. It doesn't tell you what the tension in the rope is. So you could use this equation correctly. The mass of the system is the person's mass. The change in speed of the person was 1.4. It took 2 seconds to do it. And that means that the person's action adds 28 newtons of tension to the rope, but you would be ignoring the tension that's there due to their weight. Okay, so there's a force interaction due to the acceleration of the object in addition to gravity. Okay, so it would be easy to do the right thing with the impulse momentum theorem, but make the mistake of thinking there's only 28 newtons of tension in the rope. All right, so you would have to, so I just kind of throw that out there as this is good stuff, but it's only part of the puzzle. That's why we need to draw a force diagram, and the system schema helps us make sure that we include all of the things that are relative to the problem in our force diagram. Force diagrams lead to a good system of equations, and then if you do the math right, you get the answer right, and you account for everything, not just part of the puzzle. So I think that you could easily see, no matter what discipline you're going to in the sciences, this way of thinking is absolutely critical to what you do. You need to account for everything and not trick yourself into thinking that just accounting for one thing is accounting for all of the things in the system. All right. We had the situation of a couch, and we sort of did this one the other day, and somebody applying a force to it, but there's friction involved. Friction always resists the motion, and according to this problem, the mass of the couch was 100 kilograms. The coefficient of friction was 0.15. We just went over that the other day. I'm sorry, it wasn't 0.15. It's 0.3. One of the other problems is 0.15. And we know that acceleration was 0. And the reason we knew that acceleration was 0 is it's constant speed. Okay? Because the change in speed is 0. But it is moving. All right? It has some velocity, but the change in velocity is 0. All right, so we knew that from the problem. So that'd be a way you could condense the English statement into a picture that we would subsequently abstract in some way. So we have a couch. All right. We have the ground beneath the couch. We have the person pushing on the couch, and then the earth is always involved with these sorts of things. And so the couch and the ground have a contact force. Couch is also uh, in a gravitational interaction with the earth. All right. There's also the force of friction going on there, but then there's this person in contact with the couch. And this would lead us to a force diagram. Let's see, let's stick that right there. There's the weight of the couch. There's the normal reaction force, which I have made equal and opposite. The applied force of the person, I'm making larger than the resistance force of friction because it's moving. However, they could be equal. All you have to do is basically perfectly match them. So if we wanted to, we could extend that out in size. It wouldn't be wrong to have them equal. What would be wrong is if the applied force was less than the friction force in magnitude, then you wouldn't be having motion. Okay, so either one of the ways that I've drawn it, where they're equal or the applied force is bigger, are okay. They're correct. uh, things here. And acceleration is 0 in all directions. So when I go to sum the forces, and I'm going to sum them in the y direction. So this is the first time in this problem set where we have two directions to account for. All right. And so in the y direction, there's the normal force up minus the weight force down, and it's not moving in the y direction. So what this means is the normal force equals mg. And we had gone over how the normal force isn't always mg, but it's always related to mg. Either it's a fraction of mg or I'm taking away from mg. All right. So inclined planes, it's going to be some fraction of that. And you guys are being really still out there. So that I get normal force is mg, then I sum the forces in the x direction, and I get the big force minus the friction force applied minus friction. That also equals 0 under constant speed, which means friction and the applied force are equal. So technically speaking, we should make those equal and opposite. Did that on purpose, just to kind of illustrate the way that we naturally think about it. If there's motion in a direction, you would assume that that applied force is greater than all of the resisting forces. Well, it's greater than or equal to. Okay. If it were truly greater than, then the acceleration wouldn't be 0. Right? So the fact that the acceleration is 0, the constant velocity absolutely demands that the applied force equals the resisting force. Now, the subtle truth, and you would catch this from the reading or the other problems that we've done and will do, initially, the static force of friction is bigger than the force of friction after it's moving. So static friction would require a little bit more, and then once it's moving, you could have a little bit less applied force and match the friction force. All right. Anyways, so if you recall, friction is mu times the normal force. That's the definition. These are defined that way. And the normal force is mg. And so that comes into play right there. And so we would just compute now. 0.3 times the 100 kilograms times gravity. I'll just use 10. And I'm going to use 10 newtons per kilogram. Newtons per kilogram and meters per second squared are the same thing. They're about the same thing. And so we get 300. 30% of 1,000 is going to be 300 newtons. If you use 9.8, obviously you'll get a slightly smaller number, but it's the computation that matters over anything else. So this would be the most that we can model in this situation of someone putting a lovely couch on the ground with this friction coefficient. In this situation, problem number 4, where you had the boy in a 30 kilogram sled. So here's our 30 kilogram sled. There's a tow rope, so there can be some tension in that rope. Told that the angle that it's pulled at is not 30, it's 60. So I'll crank that angle up a little bit. So 60-degree angle. And let's see, according to problem, so mass of the system we're concerned with is 30. Initial speed is 0. Final speed 2 meters per second. The time that it takes to do that is 4 seconds. So this would mean that the acceleration in the x direction is just going to be change in speed over change in time, or 0.5 meters per second squared. So that's what we can get from the overall situation. I'm going to go straight to the force diagram. So we know that there's a weight force down. We know that there's a normal reaction force straight up. We know that there's some friction moving against the tension. Now this tension is going to have, there's an x part to the tension. That would be our Tx, so it's going to be some fraction of the resolved force T. And there's going to be a Ty, or the up part of that situation. And so the trig is going to deliver for us when we get to that. So I skipped the system schema. We've done a few of those. And so here's the force diagram that's going to lead me to the right set of equations. So let's get at it. So the sum of forces in the y direction are going to be the normal force up. And since that Ty component is opposite the angle, it's going to be T sine theta. And then that's both of the up forces. And then there's one down force, mg. And all of that has to equal 0 because it's not accelerating in the y direction. The sled is staying on the ground. It's not moving up in the air. And so if it's a friction problem, we need to find the normal force. You can always count on that. Well, what do I solve for? Well, you need the normal force if it's a friction-based problem, inevitably. So this means the normal force is going to be this wonderful mg, when that moves to the other side, minus T sine theta. So we just hold on to that. We know that this is going to be important shortly. Then we sum the other direction, the x forces. Well, there's one force to the right, that's a positive force. So T cosine theta, because it's adjacent to the angle of that tension, minus the friction force. And that has to equal ma in the x direction, because we are accelerating in the x direction. It's not 0 there. And so what we're going to do now is this becomes what we're interested in, because the left-hand side of that equation is the sum of forces. And so now we just want to zero in on that piece of the puzzle. And we need to replace friction with its definition, okay, which is always mu n. And the normal force might be mg, or it might be some fraction of mg, or be some other thing. And in this case, it is a difference between the true weight and the tension in the rope, because part of the tension in the rope is kind of relieving the weight of this sled, because there's a partial pulling up there. So we would plug this in, mu times mg minus T sine theta equals ma in the x direction. So this thing up here coming in as such. So that means we need to kind of distribute all that out. So T t cosine theta minus mu mg plus mu t sine theta, because that minus of a minus is a plus, equals max. And so really everything is known in this problem except the tension in the rope. We know what the coefficient of friction is. I didn't write it, but this one was mu equals 0.15. That was stated in the problem. So we need to solve for t. So t cosine theta plus mu t sine theta will equal max plus mu mg, because that goes over the other side. So t will equal max plus mu mg over cosine theta plus mu sine theta. And if you plug and chug all that stuff into that equation, you should get 95 newtons. That would be the tension in the rope. I guess the only tough thing really about this problem would be it gets a little gnarly down there at the bottom when you get into the trig. And so the mistake you're going to make here is going to be a careless algebra mistake, assuming your equations are set up or your force diagram is set up properly. So, or maybe just fat fingering the calculator or something and getting a weird answer. So we have in problem number 5, there was a rocket. So the mass of this rocket was 4,000 kilograms. So I trust that you either remember or have the questions typed out. Remember that. The force of the thrust was 70,000 newtons. And the time frame of that thrust was 15 seconds. Now, if we were to use the impulse momentum theorem, which has 4 factors in it, 3 of which are on screen, we could compute and get a number that's correct with respect to the problem, but it wouldn't necessarily be, it could lead us astray. So I want to make sure that we're careful and then show the difference there. So let's do it. This is an object under forces. It's got a thrust force applied to it, and since it has mass, then gravity is trying to pull it down. That's why it's so hard to get things into space, is the Earth is sort of protective of objects that are near it. So there's a weight force, or mg, pressing down, and there is a much larger force, I'll call F sub t, thrust force, moving up, and it is accelerating in that direction. The net acceleration is positive in that direction. So let's sum our forces. So the sum of forces would be the big force of thrust going up minus the weight force going down is going to equal ma, which happens to be in the y direction this time. So if I put in the numbers, 70,000 minus 4,000 kilograms, and I'm going to use 10 again, newtons per kilogram, that has to equal 4,000 times acceleration in the y direction. And so that's also kilograms there. So if I solve this for acceleration in the y direction, I will get 30,000 newtons divided by 4,000 kilograms, which is just going to be 30/4 newtons per kilogram. I'll just leave it at that for the moment, which, by the way, equals 30/4 meters per second squared. So 30/4, 7.5, if we wanted to resolve that number. We'll get to that soon enough. So that would be the acceleration. It's a pretty slow acceleration. Anybody ever watched a huge rocket take off? They're kind of slow at first. By the time the bottom of the rocket clears the top of the, I think it's called a gantry, like that big frame that it's attached to, it's only going 50 or 60 miles an hour. All right. Very soon it's going to be going much, much faster than that, but initially it's kind of slow. A Saturn V rocket, which is our most common rocket for getting things up into space, I believe, it produces a thrust of about 7 million newtons. So it's 70,000 kilonewtons. All right, so this times 1,000. It also has a mass that's much, much larger. Its mass is in the millions of kilograms. So this is a really light rocket with a lot of thrust. The thrust to mass ratio on this rocket's insanely large. So this rocket's going to get up to an insane speed really fast. All right. So we have all of that. Now, I could do graphical analysis and figure out what the acceleration is, or I could say, you know what? The net force of the rocket times that change in time equals mass times change in speed. Now, here's the subtlety. So this is part of this assignment is to draw out these particulars. And the impulse momentum theorem always works when applied correctly. Any equation always works when applied correctly, but it's easy to just do equation hunting and go, I have this, that, and the other. I'm going to plug in Chugsville. All right. But what do I, if you just, because normally when we write F delta T equals M delta V, we're not thinking that that force is the net force, but technically it is. It's Newton's second law. It's the sum of forces, or the net force. And so the net force on this, so if I wanted to solve this for the change in speed, I would have net force delta T over the mass. Well, the net force is the 30,000 newtons. Okay, so very careful about this. The net force, this 30,000 newtons, that's the net force. All right. And so this change in speed will end up being 112.5 meters per second. Now, 112.5 meters per second is cooking. So if we do the conversion, which I'm going to take for granted, it's going to be roughly 252 miles per hour, since we don't deal with meters per second much in the English system. So this rocket's cooking. It's going. All right, 15 seconds. That's a lot of thrust for not a lot of mass. 70,000 newtons. That's moving and grooving. So we are able to obtain that speed. We could continue uh, the game here. We could apply the zeroth law theorem, or just we know that we have an increasing speed here. This is going to be a delta y. All right, so if I wanted to compute that, I could just use the graphical analysis instead of the zeroth law theorem, but I could use that too. That's going to be half the change in speed times the change in time, which is just going to be half. Change in speed was 112.5 meters per second for 15 seconds. And if you crunch all that out, you get 843.8 meters, roughly. So it's heading towards 9 football fields away. 100 meters is a little longer than a football field. All right. So that's a good distance in a relatively short amount of time for a small rocket under a very large thrust force. In number 6, we got a pole vaulter whose mass is 55 kilograms. The speed, just before touching the cushion, she's falling at 10 meters per second. Okay. And we know that that's the initial speed. Final speed is going to be 0. I love initial speed must have been 0 from whatever height she was at, and then sinks 0.5 meters into the cushion before falling there. So, but we can compute that the change in speed here would be 10 meters a second. Now, this means that we're defining down to be positive, the way that we've run this. It could be different. And then there is a delta y that I'm going to label as 2 because it's not the height that she fell, it's the height that she fell into, if you will, the cushion. So I'm just being clear there, trying to be. So we have a force diagram we could write. So weight of the person, there's going to be some upward force applied by the mat, and that's going to also be an acceleration opposite of the person's motion, accelerating upward. That's why it brings it to a stop, has to decelerate her. But since I defined the speed downward to be positive, this acceleration is opposite of that. All right, so let's do our graphing here. We're going to have velocity time, acceleration time. So this person obtains speed of, that was done poorly. All right, there we go. Gets up to 10 meters per second. This would be my first displacement. All right. And then over exaggerating this here, just so it's can work with it. And so we have that going on. So since that's an upslope, the change in speed for the first region, going to be a delta t1, and then there's a negative acceleration, this delta v2, for that other spot. It has to be negative because it's a downward slope. Okay, we could have flipped this. You could have had it go the other way and just kind of invert the graphs. It would be, you'd still get the same answer. All right, just running it this way here. So if I pay attention to this first displacement, that first vertical displacement would be 1/2 the change in speed during that time frame times that time frame. All right, and we would have to know what delta t1 would be, but I do know that it's going to be 1/2 of 10 times this delta t1. So it's going to be 5 delta t1. So I'll have to wait and see what happens with delta t1. Maybe I can extract that out of one of these other spots, perhaps down here in the acceleration graph. I know that it was this delta t1 would be delta v1, which I know, over a, which happens to be gravity only. So delta t1 is just going to be 10 meters per second over 10 meters per second per second. So delta t1 is just 1 second. So that means delta y1 would just be 5 meters. This right here pops up into that, and we get our answer. So we've determined how far she fell, 5 meters, how long it took to fall that rate. Probably took a little longer with air friction, okay? So, but we ignored that. So now I could pay attention to this delta y2, which would also be half delta v delta t2, all right? And we know that this was 0.5 meters. We're told that from the problem statement. We know that displacement. We know that the change in speed was the same magnitude. It was 10 meters per second. It was actually a negative 10 meters per second, but it was 10 meters per second. All right, the height of that triangle is still 10. So delta T2, we would expect this to be much smaller, and it is. You basically are going to get 0.1 second out of this, 1/10 of a second. So we know we would expect that to be the case. Obviously, it takes longer to fall from the bar to the mat than it does for the mat to stop the person. That's fast, really fast. So we would expect it to be much, much smaller than the fall. All right. And so now we can get the acceleration out of that. The acceleration for that part, for the second time interval, would just be the change in speed over that time. And the change in speed was a negative 10 meters per second. And the time was a 0.1 second. So we get an acceleration, negative in our case, of negative 100 newtons per kilogram. So what we can do is if we sum our forces like we should, we would get the force up minus the weight down equals ma, which means that the force is going to be ma plus mg, and we would just plug and chug into that. And so you're going to have a large negative force upward. Basically, the force of the mat is going to be the interaction that the vaulter has with it, plus the weight force, which is going to be, we go again with the lights, and so that'll be, some number that some 55 kilogram pole vaulter, apparently the same person, falls off a wall that's 6 meters above a 2 meter thick foam cushion resting on the ground. That would mean that the overall height is going to be 8 meters. And the reason that's important is because he, in this case, so it's not the same person, misses the cushion. Sad. So sad. And sinks 0.1 meter into the sandy ground. So thankfully this was on sand instead of concrete. So there's going to be I'll have to exaggerate it here, a change in height here of 0.1 meters, negative, below ground, if you will, which has obviously been exaggerated for sake of illustration. So if I were to draw a force diagram, as always, the mass of the thing in motion, weight force is going down. There's some force acting on this person at impact, so we're dealing with the impact in this thing, and so the ground is accelerating the person upward. So our sum of forces is going to be that up force minus mg equals ma. All right. But let's figure out a thing or two about this. So it is the case that this height would equal 1/2 gt squared. We could get this from that displacement triangle that we dealt with. The reason for that starts at 0 speed up. And so if something is at some height and just falls from rest, we can use h equals 1/2 gt squared to get either the height or the time, which we know the height. So this means the time is just going to be the square root of double the gravity constant over the height, which gives us 1.58 seconds if we want to pay attention to that. We also could determine that the speed, and I think you had this equation in some other prior homework, ends up being square root of twice gravity height. That's the zeroth law theorem boiled down from other things, and so you get 12.65 meters per second out of that, which means that's the change in speed since it started at 0. So we know the change in speed now. We know the time that it took to change that speed. And that means if we do a velocity time graph, like that, we know that that was a 0.1 meter displacement because that's the area under a velocity time graph. And so 0.1, if we apply the area rule, would equal 1/2, since this is a triangle, of the height, 12.65, times the time it took to change that height. So we get the time of the impact, the crunch into the ground. And so this computes out to a really small 0.016 seconds. We'd probably just go with 0.02 if we were doing significant digits and all that jazz. So really 2/10 of a second. I would prefer a longer impulse, okay? And so the idea of this problem is, could we, what's the force delivered to this person and in what time frame? So it's a large force, small time frame, okay? Big change in speed. So we have that time that it took for the person to experience a fair amount of pain, all right? Acceleration has to be negative because that's a downward slope, all right? So these things, all right, so our delta V would equal A delta T. So our A, just delta V over delta T, it is a negative 12.65. We get that from the graph. The time frame, 0.016 seconds, minus 800 newtons per kilogram. So realize that a 100-kilogram person, their weight is going to be basically 1,000 newtons. So the force of impact that this person feels in crunching into the ground is essentially like double their own weight. I don't want to experience the force of double my own weight. Okay? Now, I've done something stupid in my youth where you see how many people can pile into an empty van. It was a radio show contest. And at the time, I was in much, much better shape. I could lift a large amount of weights in various ways. I was pretty tough, I have to admit. And so I was on the bottom. And this was an okay thing until about, I think, the seventh person got up on top of all of us stacked in that van. And that's when I started to get a little worried. All right. Thankfully, it didn't last long, but I can tell you that was feeling the weight of 7 people on top of me, even though at the time I could bench press 350, I could get 230 off the ground from the floor, I could curl 180. I mean, I was in good shape, but a minute of 2, 3, 4, 5 people getting on you, it's hot. Your arms are getting tired because you're trying to match that. It's like a long push-up with people on you. So it was it was dumb. There was one person who got hurt. Um, that was unfortunate. Anyways, just to give you a picture of, double your own weight hitting you. That's what it would be like if you were this person who fell 8 meters, which is a long ways, okay, into anything that isn't a big old cushion.